Hello and welcome. Tonight we're going on a quiet journey together, one that asks a simple question you probably never stop to think about. Are you moving right now? You might say no. You're sitting lying down perfectly still. But here's the thing. You've never been still. Not for a single breath. Not for a heartbeat. Not since the day you were born. Right now as you rest, you're spinning through space faster than a bullet. Faster than sound. Faster than anything you've ever felt, and you don't feel a thing. The earth beneath you is moving in ways so vast, so ancient, that even scientists still whisper in wonder when they measure it. We are passengers on a ship we never boarded, drifting through an ocean we cannot see. So, tonight before you sleep, let's drift together. Let's follow the earth as it spins, orbits, tumbles, and falls through the universe. Let's trace the invisible dance that carries us all. You don't need to understand everything. Just rest. And let curiosity do the listening. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe, if you'd like more stories told softly. And ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. Some nights when the world grows quiet, you might look up and feel small. The stars seem fixed, eternal, unchanging. But that stillness, it's an illusion. The most beautiful lie the universe ever told. Because nothing in the cosmos stands still. Not the stars, not the galaxies, not even you. Right now, you are hurtling through space at speeds that would make a fighter jet look slow. But you feel nothing. The air around you doesn't rush past your face. Your coffee doesn't spill. The stars don't blur into streaks of light. Why? Because motion, when shared, becomes invisible. Let's start with something simple, something we all know but rarely think about. The ground beneath your feet, it feels solid, permanent, trustworthy. But that ground is part of a planet, and that planet is spinning. Scientists tell us the Earth rotates once every 23 hours, 56 minutes, and 4 seconds. Not 24 hours close, but not quite. That missing 4 minutes, it adds up. It's why we need leap years, those strange extra days that keep our calendars aligned with the seasons. But here's what makes you pause at the equator. The surface of the Earth is moving at about 1,040 miles per hour. That's faster than the speed of sound. If you're standing in Ecuador or Kenya or the islands of Indonesia, you are breaking the sound barrier just by standing still. And yet, you feel nothing. Move toward the poles and the speed drops. In London, it's about 650 miles per hour. In Alaska, maybe 500. At the very top of the world at the North Pole, you'd be spinning in place, turning slowly like a figure on a music box, but barely moving forward at all. It's not the speed that changes. It's the distance you travel in a single rotation. The Earth is widest at the equator, so you cover more ground. Near the poles, the circle is smaller. The spin is the same. The journey is shorter. This is one of the universe's quiet tricks. Speed depends on where you stand. But if we're moving so fast, why don't we feel it? Why don't we fly off into space like water shaken from a dog's coat? The answer is gravity and inertia. And the fact that everything around you, the air, the trees, the oceans, the clouds, is moving with you at exactly the same speed. When you're inside, motion disappears. Think of it like this: when you're in a car on a smooth highway moving at 60 miles per hour, you don't feel like you're moving. You can sip your coffee, read a book. The world inside the car feels still. It's only when the car changes, speed accelerates, brakes, turns, that you feel it. The Earth is that car, and it's been moving at the same speed in the same direction for over 4 billion years. So smooth, so constant, that to us, it feels like stillness. But here's where it gets even stranger. The Earth doesn't just spin, it wobbles. Scientists call it precession. Imagine a spinning top slowly tracing a circle as it spins. That's what the Earth does. Its axis, the invisible line running from the North Pole to the South Pole, doesn't point in exactly the same direction forever. It drifts, slowly, gently, like a compass needle pulled by an unseen magnet. Right now, the North Pole points toward a star we call Polaris, the North Star. Sailors used it for centuries to navigate. It seemed eternal, fixed the one constant in a turning sky. But 5,000 years ago, the North Pole pointed toward a different star, Thuban in the constellation Draco. And 12,000 years from now, it will point toward Vega, one of the brightest stars in the summer sky. The axis completes one full wobble every 26,000 years. A cosmic clock ticking slowly, patiently, long after empires rise and fall. This wobble also shifts the seasons very slightly over millennia. It's one reason why ancient calendars, Egyptian, Mayan, Babylonian, needed constant adjustment. The stars were moving, or rather we were, and they had to account for it. But even that wobble is just one layer of the dance. There's another motion, subtler still. Scientists call it nutation. It's a small nod, a tiny tremor in the Earth's spin, caused by the moon's gravity tugging unevenly on our planet's bulging equator. The Earth doesn't just wobble, it shivers. And there's the Chandler wobble, named after the astronomer who discovered it in 1891. The Earth's axis doesn't just point in one direction as it spins. It traces a tiny circle about 30 feet wide every 433 days. No one knows exactly why. Some think it's caused by pressure changes in the ocean. Others suggest motion deep in the Earth's core. Even the ground beneath us holds mysteries. But let's step back. Let's return to that first question. Why don't we feel any of this? Part of it is scale. When something is enormous, its motion can be both vast and gentle. A cruise ship can move through the ocean at 20 miles per hour, and passengers inside barely notice. The Earth is so much larger. Its motion so much faster. And yet it carries us so smoothly that even a feather resting on a windowsill stays perfectly still. Part of it is also atmosphere. The air around the Earth spins with it. If it didn't, we'd experience winds beyond imagination, permanent hurricanes tearing across the surface at over 1,000 miles per hour. But the air moves with us. It's caught in the same invisible grip of rotation. So, to us, the air feels calm, and part of it, maybe the deepest part, is simply this. We've never known anything else. You were born into this motion. You grew inside it. Every breath you've ever taken, every step you've ever walked, every dream you've ever dreamed, it all happened while you were spinning. Motion is your natural state. Stillness would be the strange thing. But here's the beautiful part. Even though we don't feel it, we see it. Every sunrise is evidence. Every sunset proof. The stars wheel across the sky, not because they're moving, but because we are. Ancient people saw this and imagined the heavens rotating around us, a great celestial sphere, turning slowly, carrying the sun and moon and stars in an eternal loop. They weren't wrong to think that. When you watch the sky long enough, it really does look like the universe is spinning around the Earth. It's one of the most convincing illusions nature ever made. It took centuries, millennia for us to realize the truth, that the sky isn't moving, we are. And when that realization finally came, it shattered everything people thought they knew about their place in the cosmos. In the early 1600s, a man named Galileo Galilei pointed a telescope at the planet Jupiter and saw something no one had ever seen before: 4 small moons orbiting the giant planet like a miniature solar system. He watched them night after night, tracing their paths, measuring their motion. And he realized if moons can orbit Jupiter, then maybe the Earth isn't the center of everything. Maybe we orbit the sun. The idea wasn't new. A Polish astronomer named Copernicus had suggested it decades earlier. But Galileo had proof, evidence, something you could see with your own eyes. The church didn't like it. They called him to Rome, threatened him, forced him to recant. He spent the last years of his life under house arrest, forbidden from teaching, forbidden from publishing. But the truth was already out. The Earth moved, and no amount of denial could stop it. Some say Galileo whispered after his trial, and yet it moves. Whether he really said it or not, the sentiment was true. The earth spins, and no belief, no decree, no refusal to accept it could change that fact. We are passengers on a spinning world. Always have been, always will be. But spinning is just the beginning, because the earth doesn't just turn in place like a ballerina. It's also falling through space endlessly in a graceful arc around the sun. And that fall, that second motion, is what gives us seasons, years, and the passage of time itself. The spin gives us day and night. The orbit gives us everything else. So, the earth spins. We've established that. A quiet rotation invisible to us, but undeniable. Day fades to night. Night returns to day. The rhythm never breaks. But there's another motion happening at the same time, a bigger one, a motion so vast that it takes an entire year to complete. The earth is falling, not crashing, not plummeting out of control, but falling nonetheless in a long, graceful arc around the sun. Scientists call it an orbit. Poets might call it something else. A waltz, perhaps. A dance that's been going on for 4.5 billion years. And right now, as you listen to this, you're traveling through space at about 67,000 miles per hour. That's 18 miles every second. Faster than any rocket humanity has ever built. Faster than the speed of thought it sometimes feels. And yet, like the spin, you feel absolutely nothing. The orbit is what gives us our year, our seasons. The slow turn of spring into summer, autumn into winter. Without it, there would be no harvest, no migration, no reason to mark time at all. But here's the part most people get wrong. Many of us grew up thinking that summer happens because the earth is closer to the sun. It makes sense, doesn't it? Closer equals warmer, farther equals colder. Simple. But it's not true. In fact, the earth is closest to the sun in early January, right in the middle of winter for the northern hemisphere. And it's farthest from the sun in early July when summer blazes across North America and Europe. So, if distance isn't the reason, what is? The answer is tilt. The Earth doesn't spin upright like a perfectly balanced top. It leans. The axis, the invisible line running from pole to pole, is tilted at an angle of about 23.5 degrees, and it stays tilted in the same direction as the Earth orbits the sun. When the northern hemisphere is tilted toward the sun, sunlight strikes it more directly. The rays come in at a steeper angle, concentrating their warmth. Days grow longer, nights grow shorter. We call it summer. 6 months later, the Earth is on the opposite side of its orbit. Now, the northern hemisphere tilts away from the sun. Sunlight comes in at a shallow angle, spreading thin across the surface. Days shorten, nights lengthen. Winter arrives. Meanwhile, the southern hemisphere experiences the opposite. When it's summer in New York, it's winter in Sydney. When autumn leaves fall in London, spring blossoms open in Buenos Aires. The tilt is everything. Without it, there would be no seasons. Just an endless, unchanging sameness, warm at the equator, cold at the poles, and moderate in between. Life, as we know it, might not exist. But why is the Earth tilted in the first place? Scientists believe it happened early in the planet's history, about 4.5 billion years ago, when the solar system was still young and chaotic. A Mars-sized object, sometimes called Theia, slammed into the Earth in a collision so violent that it melted the surface and sent debris spinning into space. That debris eventually coalesced into the Moon. And the impact knocked the Earth off its axis, giving it that 23.5-degree tilt. A cosmic accident that became the foundation of all earthly life. The crash that gave us seasons. If the tilt were different, everything would change. If the Earth stood perfectly upright, there would be no seasons at all, just permanent climates in every region. If the tilt were more extreme, say 45 degrees or more, the seasons would become harsh, almost uninhabitable. Summers, scorching winters, frozen solid. But 23.5 degrees. It's just right, enough variation to create seasons. enough stability to support life. The orbit itself is not a perfect circle. It's an ellipse, a stretched out oval with the sun sitting slightly off-center. At its closest point, called perihelion, the Earth is about 91, 4 million miles from the sun. At its farthest point, aphelion, it's about 94.5 million miles away. That's a difference of about 3 million miles. It sounds like a lot, but in the vastness of space, it's barely noticeable. The change in sunlight from perihelion to aphelion is only about 6 or 7%, not nearly enough to cause the seasons. Still, it does have small effects. Winters in the northern hemisphere are slightly milder because the Earth is closer to the sun during that time. And summers in the southern hemisphere are slightly warmer for the same reason. But the tilt dominates everything. Now, here's another strange detail. Most people never think about the Earth's orbit isn't constant. It changes, slowly. Over tens of thousands of years, the shape of the orbit shifts. Sometimes it becomes more circular, sometimes more elliptical. This is part of what scientists call the Milankovitch cycles, named after the Serbian scientist who discovered them in the early 1900s. These cycles affect how much sunlight reaches different parts of the Earth, and they're one of the reasons ice ages come and go. Right now, the Earth's orbit is relatively circular, but 100,000 years ago, it was more stretched out. And that small difference combined with changes in the tilt and wobble of the axis was enough to plunge the planet into an ice age. Even the climate, it turns out, is written in the geometry of our orbit. But let's return to the speed. 67,000 miles per hour. That's how fast the Earth is traveling around the sun. And yet, from our perspective, the sun seems to move slowly across the sky. It rises gently in the east. It sets softly in the west. There's no sense of rushing, no feeling of velocity. Why? Because the orbit is enormous. The path the Earth traces around the sun is about 584 million miles long. Completing that journey in 1 year means moving very, very fast. But because the circle is so large, the curve is gentle, imperceptible, like walking along the edge of an ocean so vast that the horizon never seems to bend. And here's something even stranger, the sun isn't standing still either. We think of the sun as fixed as the center of our solar system, unmoving, while the planets dance around it. And in a way that's true. But the sun is also moving, dragged by the gravity of the planets orbiting it. When Jupiter, the largest planet, swings around the sun, it pulls the sun slightly off-center. Not much, just a little wobble, a tiny shift in position. But it's there. The sun and Jupiter orbit a common center of gravity, a point that lies just outside the sun's surface. So even the sun is dancing. Even the center moves. This is how astronomers find planets around other stars. They watch for that wobble, the telltale sign that something massive is pulling on the star, something they can't see directly. A planet hidden in the light. The universe is full of motion within motion, circles within circles. Nothing is truly still. But back to the Earth, back to this 67,000 mile per hour journey around the sun. One orbit takes 365 days, 5 hours, 48 minutes, and 46 seconds. Not 365 days exactly. That extra quarter of a day adds up. After 4 years, we've gained almost a full day. So we add it back, February 29th, the leap day. The Romans knew this. Julius Caesar introduced the Julian calendar in 45 BCE, with a leap year every 4 years. It worked well, but not perfectly, because the year isn't exactly 365.25 days long. It's about 11 minutes shorter. 11 minutes doesn't sound like much, but over centuries those minutes add up. By the 1500s, the calendar had drifted 10 days out of sync with the seasons. Spring equinox, which was supposed to fall on March 21st, was happening on March 11th instead. So, in 1582, Pope Gregory XIII introduced a new calendar, the Gregorian calendar, the one we still use. He skipped 10 days to correct the drift. And he added a new rule: leap years happen every 4 years, except in years divisible by 100, unless the year is also divisible by 400. So the year 1900 was not a leap year, but the year 2000 was. It's a strange little quirk, a patch in the code of time, but it keeps us aligned with the seasons even as the Earth spins and orbits and wobbles through space. And here's a question worth asking. What would happen if the Earth's orbit changed? What if something knocked us closer to the sun or farther away? If we moved just 5% closer, temperatures would rise dramatically, the ice caps would melt, oceans would evaporate. The Earth might become another Venus hot hostile wrapped in thick clouds of carbon dioxide. If we drifted just 5% farther, temperatures would plummet, the oceans would freeze, the atmosphere would thin. We'd spiral into a permanent ice age or worse. The orbit we have, this specific distance, this specific speed, is a kind of miracle. Not because it was designed, but because it happened to fall in a narrow range where liquid water can exist, where life as we know it can survive. Astronomers call this the habitable zone, the Goldilocks region, not too hot, not too cold, just right. And we're in it, spinning and falling at just the right speed, at just the right distance, tilted at just the right angle. But the orbit doesn't just carry us through space. It also carries us through time. Every sunrise marks another turn of the Earth. Every year marks another lap around the sun. We measure our lives by these rhythms: birthdays, anniversaries, seasons of growth and decay. The Earth moves and we move with it, bound to its motion, shaped by its dance. But even this, the spin, the orbit, the tilt, is only part of the story. Because the Earth and the Sun are not drifting alone through the void. They're part of something much larger, something ancient, something vast beyond imagining. The solar system itself is moving. And where it's going, well, that's a journey measured not in years, but in millions of them. The Earth spins, the Earth orbits. Two motions perfectly synchronized like a figure skater, spinning while gliding across ice. But what if I told you the ice itself is moving? What if the entire rink, the sun, the planets, the asteroid belt, everything we call the solar system is flying through space at over 500,000 miles per hour? It is. Right now, as you rest, the sun is carrying us on a journey so immense that it takes 230 million years to complete. A single lap around the center of our galaxy, the Milky Way. Astronomers call it a cosmic year. And in that time, entire species rise, flourish, and vanish from the Earth. The last time our solar system was in this exact spot in the galaxy, dinosaurs had just begun to walk the Earth. The continents looked different. The climate was warmer. There were no flowers yet, no grass, just ferns and cycads and conifers stretching across Pangaea, the ancient supercontinent. And here we are again, returned to the same cosmic address 230 million years later. But everything has changed. The solar system doesn't sit still in space. It moves. And not in a straight line, but in a great sweeping arc, in orbit around something far more massive than the sun could ever be. At the heart of the Milky Way, about 26,000 light-years from where we are now, there sits a supermassive black hole. Scientists call it Sagittarius, a star pronounced A star. It's about 4 million times the mass of our sun, and it holds the entire galaxy in its gravitational grip. Everything in the Milky Way orbits this black hole. Stars, gas clouds, entire solar systems, all of them caught in the same slow cosmic waltz. We're just one dancer among billions, moving to a rhythm set by gravity itself. But unlike the Earth's orbit around the sun, which takes a single year, our orbit around the galaxy takes an almost incomprehensible amount of time. 230 million years, longer than mammals have existed. Longer than the Atlantic Ocean has been open, longer than the Appalachian Mountains have stood. In the entire history of complex life on Earth, the solar system has only completed about 20 of these galactic orbits, 20 laps around the Milky Way. That's all. And each lap, scientists estimate, takes us through different regions of the galaxy regions with different densities of stars, different amounts of cosmic radiation, different risks of nearby supernovae. Some researchers believe these changes might even influence life on Earth, triggering ice ages or mass extinctions when we pass through denser, more dangerous parts of the galaxy. It's still debated, still uncertain, but it's one of those beautiful questions science hasn't fully answered, yet does our position in the galaxy shape the story of the life itself? Now let's talk about speed. The solar system is moving at about 514,000 miles per hour relative to the center of the Milky Way. That's 143 miles per second. Faster than anything humanity has ever built. Faster than the Voyager probes, which are the most distant human-made objects in space, traveling at a mere 38,000 miles per hour. We are outracing our own spacecraft by more than 10 times. And yet, just like the spin of the Earth and the orbit around the Sun, we feel none of it. Because everything around us, the Moon, the planets, the Sun, even the space between, is moving with us, locked together by gravity, drifting as one. But here's where it gets strange. The solar system doesn't orbit the galaxy the way the Earth orbits the Sun. It doesn't trace a neat flat circle. Instead, it bobs up and down as it moves, rising above the galactic plane and then dipping below it like a horse on a carousel that's also spinning. Scientists call this motion galactic oscillation. The solar system completes one full up and down cycle roughly every 64 million years. And some researchers have noticed something curious. Many of the Earth's mass extinctions seem to happen around the times when we pass through the galactic plane. Coincidence? Maybe. Or maybe there's more radiation, more gravitational disturbances, more comets jostled out of the distant Oort cloud when we're moving through the thickest part of the galaxy. The evidence isn't conclusive, but it's enough to make you wonder. The galaxy is not empty space. It's full of stars, full of dust, full of invisible forces we're only beginning to understand. And as we travel through it, we're brushing against things, encountering things, changing ever so slightly because of where we are and where we've been. Think about it. The solar system is about 4.6 billion years old. In that time, it has circled the galaxy about 20 times. Each orbit exposes us to different stellar neighborhoods, different clouds of gas and dust, different gravitational influences. Some of those encounters have been violent. There's evidence that about 2.7 million years ago, a nearby star passed close enough to disturb the Oort cloud, a vast distant shell of icy objects surrounding the solar system. That disturbance may have sent a shower of comets tumbling toward the inner solar system, some of which might have struck the Earth. Was one of those comets responsible for an ice age? For a shift in climate that changed the course of evolution? We don't know, but the possibility is there, written in the motion of the stars. Now here's something most people never realize: the Sun is not moving alone. It's surrounded by a neighborhood of stars, hundreds of them, all moving in roughly the same direction, at roughly the same speed. Astronomers call this the local bubble, a region of space about 1,000 light-years across, carved out by ancient supernovas that swept away most of the gas and dust. We're inside that bubble, and the bubble itself is moving through the galaxy, carried along by the rotation of the Milky Way. So even our neighborhood is in motion, part of a larger flow, a cosmic river of stars. And the Sun. The Sun is middle-aged, about halfway through its life. It formed in a stellar nursery, a dense cloud of gas and dust, along with thousands of other stars. But over billions of years, those sibling stars have drifted apart, scattered across the galaxy by gravitational interactions and the slow churn of galactic rotation. Somewhere out there, moving through different parts of the Milky Way, are stars that were born at the same time as the Sun, from the same cloud of gas. We'll probably never know which ones they are. They're too far away now, lost in the vastness of the galaxy, but they're out there, distant cousins moving on their own paths. Does that make you feel small, or does it make you feel connected? Both maybe, That's the paradox of astronomy. The universe is so large that we seem insignificant, and yet we're part of it, made from it, bound to its rhythms and motions and cycles. Now, let's consider this. What if the solar system's orbit around the galaxy were different? What if we were closer to the center or farther out? If we were too close, say, within a few thousand light years of the galactic core, the environment would be hostile. The density of stars would be much higher, meaning more frequent close encounters, more risk of gravitational disruptions. Radiation levels would be intense, bombarding any planets with high-energy particles. And the supermassive black hole at the center, Sagittarius, a star, would dominate the sky, a dark presence consuming everything that drifted too near. Life as we know it probably couldn't survive there. If we were too far out, say in the outer reaches of the galaxy where stars are sparse and the space between them is vast, the environment would be quieter, but also poorer in heavy elements. Stars in the outer galaxy tend to be older, made mostly of hydrogen and helium, with very little of the carbon, oxygen, nitrogen, and iron that life needs. The planets that form around those stars are more likely to be gas giants with few rocky worlds. And without rocky worlds, there's no place for life to take root. But here where we are, about 26,000 light years from the center in what astronomers call the galactic habitable zone, the conditions are just right. Enough heavy elements to form rocky planets, enough distance from the galactic core to avoid the worst radiation, enough nearby stars to enrich the neighborhood with supernovae which create and scatter the elements life depends on. We're in the Goldilocks zone again, not just around the sun, but around the galaxy itself. Coincidence or something deeper? Some scientists suggest that life might only be possible in these narrow regions of a galaxy, that intelligent civilizations, if they exist, would almost certainly arise in similar places. Orbital distances, star types, galactic neighborhoods. The universe might be full of life, but only in the right places, only where the motion and the chemistry and the timing all align. And we're here, moving through one of those places, spinning and orbiting and circling all at the same time. But the motion doesn't stop there, because the Milky Way itself is not stationary. It's moving too, and it's not alone. Across the void, another galaxy is approaching, slowly, inevitably. And when it arrives, everything, the stars, the solar system, the shape of the night sky will change. The Milky Way is moving, not just rotating, not just spinning its spiral arms through space. It's traveling, falling in a way, drawn by something vast and ancient, something written in gravity's oldest language. On clear nights far from city lights, you can sometimes see it, a faint smudge of light in the constellation Andromeda. It doesn't look like much, a soft glow easily missed if you're not looking for it. But that smudge is a galaxy, an entire galaxy, 2.5 million light years away. And it's coming toward us, not slowly, not gently. The Andromeda galaxy is rushing toward the Milky Way at about 250,000 miles per hour. And in roughly 4.5 billion years, the two galaxies will collide. It sounds violent, doesn't it? A collision, a crash. Two massive objects meeting in the dark. But galaxies don't collide the way cars do. They pass through each other like ghosts. Stars are so far apart that even when galaxies merge, individual stars almost never touch. Still, everything changes. The Andromeda galaxy is bigger than the Milky Way. It contains about 1 trillion stars compared to our few hundred billion. It's been traveling toward us for billions of years, pulled by the mutual gravity between the two galaxies. And we're traveling toward it too. Both of us falling toward a future that neither can escape. Astronomers have known about this for decades. In 1912, an American astronomer named Vesto Slipher measured the light coming from Andromeda and noticed something strange. The light was blue shifted toward shorter wavelengths, which meant Andromeda was moving toward us, not away like most galaxies. At the time, no one knew what it meant. Was Andromeda special, or was something else going on? It took years to figure out, But eventually, astronomers realized Andromeda and the Milky Way are gravitationally bound. We're part of the same local group of galaxies orbiting a common center of mass. And because Andromeda is more massive, it's pulling us toward it with a force we cannot resist. Think of it like two dancers moving toward each other across a darkened stage, slowly at first, then faster, until they meet in the center, spinning together, becoming something new. Scientists have run simulations of what will happen, computer models that track the motion of billions of stars over billions of years. And the results are both beautiful and strange. At first, the two galaxies will pass close to each other. The gravitational pull will distort their shape, stretching them, pulling long tidal tails of stars out into space. The Milky Way's spiral arms will warp. Andromeda's disk will ripple. Then they'll swing around each other like trapeze artists catching hands in midair and fall back together. This time, the collision will be more direct. The cores of the two galaxies will merge. Stars will scatter. Some will be flung out into intergalactic space, orphaned, doomed to drift alone in the void. Others will settle into new orbits, forming a new structure, a giant elliptical galaxy, no longer spiral, no longer flat. Astronomers have already given it a name, Milkomeda. But here's the part that makes you pause. Even though the galaxies will collide, the stars themselves will almost certainly survive. The distances between stars are so vast that the chance of two stars actually hitting each other is almost zero. Instead, the stars will simply find themselves in new orbits under new rules, part of a new cosmic order. The sun might be flung farther from the galactic center, or it might drift closer. The night sky will change, new constellations, new neighbors, a new arrangement of light. But the Earth, if it still exists by then, it will likely be fine. The solar system will continue orbiting the sun just as it always has. The planets won't crash. The moon won't fall. Life, if it still clings to the surface, might not even notice. Though by that time, the sun will be nearing the end of its life. In about 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, possibly even the Earth. So, the collision with Andromeda might happen just as the sun is dying, two cosmic events perfectly timed, closing the chapter on everything we've known. But let's step back. Let's return to the present. Right now, Andromeda is 2.5 million light-years away. That means the light we see from it tonight left the galaxy 2.5 million years ago, back when early humans were just beginning to use stone tools. When we look at Andromeda, we're seeing the past. Not the galaxy as it is now, but as it was when light first started its long journey toward us. And Andromeda is seeing us the same way, or would be if there were anyone there to look. They would see the Milky Way as it was 2.5 million years ago. A younger galaxy, a different arrangement of stars. This is one of the strange truths of the universe. Distance and time are woven together. To look across space is to look back in time. The farther away something is, the older the light we receive from it. Now, here's a question. How do we know Andromeda is approaching? How can we measure the speed of something so far away? The answer lies in light, specifically in something called the Doppler effect. You've probably experienced the Doppler effect with sound. When an ambulance races toward you, its siren sounds higher in pitch. When it moves away, the pitch drops. The sound waves get compressed as the source moves toward you and stretched as it moves away. Light works the same way. When an object moves toward us, its light waves get compressed, shifting toward the blue end of the spectrum blue shift. When it moves away, the waves stretch out, shifting toward the red shift. Most galaxies in the universe are redshifted. They're moving away from us, carried by the expansion of space itself. But Andromeda blue shifted, moving toward us, defying the general flow. That's because gravity at this scale is stronger than expansion. The pull between the Milky Way and Andromeda is enough to overcome the stretching of space. We're bound together, falling toward each other, and nothing can stop it. Unless, of course, something unexpected happens. Scientists have considered the possibilities. What if a third galaxy passes by and disrupts the collision? What if dark matter, the invisible substance that makes up most of the mass in the universe, is distributed differently than we think, changing the gravitational dynamics? It's possible. The universe is full of surprises, but based on everything we know, the collision is inevitable, written in the mathematics of motion, unavoidable, and it's not just Andromeda. The entire local group, the cluster of about 54 galaxies that includes the Milky Way and Andromeda, is gravitationally bound. Triangulum, the third largest galaxy in the group, is also part of the dance. It might merge with Andromeda before Andromeda reaches us. Or it might join the collision later, adding its stars to the mix. Everything in the local group is moving, falling, drawn together by gravity's slow, patient hand. But here's the part that feels almost surreal. We will never see it happen. Humanity, if it still exists 4 billion years from now, will be so different that we can barely imagine it. Our species is only about 300,000 years old. In 4 billion years, evolution will have carried life on Earth, if there is any, into forms we can't even begin to picture. And yet, the collision is already happening in a sense. The light we see from Andromeda tonight has already traveled for millions of years. The galaxy we're looking at is already closer than it appears, already falling. Time is strange like that. The future and the past overlap. Motion happens on scales so vast that a human lifetime is less than a blink. Still, there's something strangely comforting about it. The idea that the universe has a plan of sorts, that galaxies dance even if the dance takes billions of years, that nothing is permanent but nothing is lost either, just transformed, rearranged, woven into something new. Milkomeda, a name that sounds almost gentle, almost soft. A merging, not a destruction, 2 galaxies becoming one. But even Milkomeda will not last forever, because the universe is not standing still. Space itself is expanding, and the local group, the Milky Way. Andromeda Triangulum, all the small dwarf galaxies orbiting them, is an island, a small cluster of gravity-bound galaxies surrounded by an ever-widening sea of emptiness. Beyond the local group, other galaxies are drifting away. The expansion of space is accelerating, driven by something scientists call dark energy. And as space expands, the distance between galaxy clusters grows. Eventually, billions of years from now, the local group will be alone, isolated, cut off from the rest of the universe. Future astronomers living in Milkomeda, if there are any, will look out into the night sky and see almost nothing. No distant galaxies, no evidence of the larger cosmos, just their own island of stars floating in an ocean of dark. They might never know that the universe was once full of galaxies. That space was once teeming with light. Unless, of course, they find records, messages, evidence left behind by earlier civilizations like us, who saw the universe in its youth when galaxies were still close enough to see. It's a strange thought, that we are living in a special time, a time when the universe is still young enough, still connected enough that we can look out and see its full scope. A time when the dance between galaxies is still visible, still happening. But that time is ending, slowly, gently. The way all things end in the universe, not with violence, but with distance, with silence, with the slow drift into isolation. And yet, even as galaxies pull apart, some are still falling together, still drawn by gravity's ancient call, still dancing even as the music fades. So, the Milky Way and Andromeda are falling toward each other, 2 galaxies locked in a gravitational embrace that will take billions of years to complete. But they're not alone. Around them, like children circling their parents, dozens of smaller galaxies orbit and drift. Dwarf galaxies, most of them. Tiny by cosmic standards, containing only a few billion stars, sometimes less. They have names like the Large Magellanic Cloud, the Small Magellanic Cloud Triangulum, the Sagittarius Dwarf. Together, all these galaxies, the big ones and the small ones, form what astronomers call the local group. a cluster of about 54 galaxies all bound together by gravity, all moving through space as a single cosmic family. And the entire family is drifting, not just orbiting each other, not just falling together, but moving as a whole towards something distant, something massive, something we can't even see directly. Astronomers call it the Great Attractor, and it's pulling us along with thousands of other galaxies toward a region of space about 150 million light years away, at a speed of roughly 1.3 million miles per hour. The Great Attractor was discovered in the 1970s when astronomers began mapping the motion of galaxies across the sky. They expected galaxies to be moving randomly scattered by the expansion of the universe, but instead they found patterns, flows, rivers of galaxies all moving in the same direction, as if drawn by an invisible hand. Something out there hidden behind the plane of the Milky Way, hidden in a region astronomers call the zone of avoidance, where dust and stars block our view. Something massive is pulling everything toward it. For years, scientists couldn't see what it was. The Milky Way itself was in the way, like trying to see through a forest when you're standing inside it. But eventually, using radio telescopes and infrared observations that can pierce through dust, they began to map the structure. What they found was astonishing. The Great Attractor is not a single object. It's a region, a massive concentration of galaxy clusters, so dense and so large that its gravity dominates the motion of everything around it. And beyond even that, there's something larger, still the Shapley supercluster, one of the most massive structures in the observable universe containing tens of thousands of galaxies. We're being pulled toward all of it. The local group, the Milky Way. Andromeda, everything. Drawn by gravity on scales so vast that the journey will take billions of years, far longer than the sun will live, far longer than the Earth will remain habitable. But here's the strange part, even though we're being pulled, we're also being pushed. Because space itself is expanding. The universe is growing, stretching the distances between galaxy clusters. And the farther apart things are, the faster they move away from each other. So we have two forces at work, gravity pulling us toward the Great Attractor, and expansion pushing everything away from everything else. Which force wins? It depends on distance. Within the local group, gravity dominates. The galaxies are close enough that their mutual attraction is stronger than the expansion of space. That's why Andromeda is moving toward us, not away. That's why the dwarf galaxies orbit the Milky Way, instead of drifting off into the void. But beyond, the local group expansion takes over. Galaxies that aren't gravitationally bound to us are moving away, and the farther they are, the faster they recede. Eventually, they'll move so far and so fast that their light will never reach us again. They'll cross a horizon we can never follow. The local group is an island, a small patch of space where gravity still holds things together, where galaxies can still meet, still merge, still interact. But around us, the ocean of space is growing, and eventually every other island will disappear beyond the horizon, leaving us alone. Unless we drift far enough, fast enough to join something larger before that happens. And that's where the Great Attractor comes in. Scientists now understand that the Great Attractor is part of an even larger structure called the Laniakea supercluster. The name comes from Hawaiian meaning immeasurable heaven. It's a vast web of galaxies stretching across 520 million light years of space, containing about 100,000 large galaxies and an estimated 100 quadrillion stars. And the local group. It sits on the outskirts of Laniakea, near the edge, being gently pulled toward the center. This motion, this drift, was mapped in 2014 by a team of astronomers led by Brent Tully. They used a new technique to measure not just how fast galaxies are moving, but in what direction. And what they found was a vast cosmic watershed, with galaxies flowing like water toward gravitational basins, the densest, most massive regions of space. The local group is part of that flow. We're a drop of water in a river that's been flowing for billions of years. and the river is carrying us toward a future we can barely imagine. But here's the question: will we ever get there? The answer most likely is no. The expansion of space is accelerating, something called dark energy, a mysterious force that makes up about 68% of the universe is pushing space apart faster and faster. And as space expands, the pull of the great attractor weakens. The distance grows. The journey becomes longer. At some point, billions of years from now, the expansion will overcome the attraction. We'll stop drifting toward the great attractor and start drifting away from it. The flow will reverse. The river will dry up, and the local group will find itself truly alone, cut off from the rest of the universe, a small island of stars in an ever-widening sea of darkness. But before that happens, we have time, billions of years. And in that time, the local group will continue to evolve, to change, to dance. Right now, the Milky Way is in the process of consuming smaller galaxies. The Sagittarius dwarf elliptical galaxy, for example, is being torn apart by the Milky Way's gravity. Streams of stars from the Sagittarius galaxy are scattered across the sky, slowly merging with our own. In a few 100 million years, it will be completely absorbed, gone, integrated into the Milky Way's spiral arms. This is called galactic cannibalism, and it's common. Most large galaxies, including the Milky Way and Andromeda, have grown by eating smaller galaxies over billions of years. The stars in the outer halo of the Milky Way, the faint diffuse cloud of stars surrounding the main disk, many of them came from dwarf galaxies that were devoured long ago. In fact, when astronomers look closely at the orbits of stars in the Milky Way's halo, they can sometimes reconstruct the history. They can identify groups of stars that move together in the same direction with the same speed. These are the remnants of ancient galaxies, ghosts of structures that once existed, now scattered and mixed into our own. It's like archaeology, digging through the stars, finding clues, piecing together a history that happened billions of years ago. And it's happening everywhere. Andromeda is cannibalizing its own satellites. Triangulum might be next. The dance of galaxies is not just a dance of merging, it's also a process of consumption. The big eating, the small, the strong absorbing the weak. It sounds harsh, doesn't it? Almost cruel, but it's simply gravity playing out over unimaginable spans of time. There's no malice in it, no intention. Just the slow, patient work of attraction, of falling, of merging, and in a strange way, it's how galaxies grow. How they build up mass, how they become the grand spiral structures we see today. The Milky Way wasn't always this large. Billions of years ago, it was smaller, simpler. But over time, it absorbed other galaxies. And with each merger, it grew, changed, evolved. You might wonder, does this affect us? Does the merging of galaxies, the consumption of dwarf galaxies, change anything about life on Earth? The answer is no. Not directly. The stars are too far apart. Even when galaxies merge, individual stars pass by each other like ships in the night. The chance of a collision is almost zero, but indirectly maybe. Some scientists suggest that when the Milky Way absorbs a dwarf galaxy, the gravitational disturbances might stir up the Oort cloud, that distant shell of comets surrounding the solar system. If enough comets are jostled loose, some might fall toward the inner solar system, toward the sun, toward Earth. And if one of those comets strikes the Earth, well, we know what can happen. The asteroid that ended the age of dinosaurs 66 million years ago might have been triggered by a similar disturbance, a distant gravitational nudge sending a rock tumbling out of the dark into our path. It's speculation. We don't know for sure, but the idea is there that even on the scale of galaxies' motion has consequences, that the drift of the local group, the merging of galaxies, the slow consumption of smaller structures, all of it in some small way might touch our lives, might shape the story of life on Earth. Or maybe not. Maybe we're too small, too isolated, too protected by the vastness of space to be affected by these cosmic events. Either way, the motion continues. The local group drifts. The galaxies spiral and merge. The great attractor pulls and dark energy pushes, and somewhere in the balance between the two, we find ourselves. Moving. Always moving. Have you ever thought about what it means to belong to something larger than yourself? To be part of a family, a community, a structure you didn't choose but can't escape? That's what the local group is. A family of galaxies bound together, moving together whether we like it or not. And maybe that's the deepest truth of all, that nothing in the universe moves alone. Everything is connected. Everything is part of a flow, a current, a drift that started long before we existed and will continue long after we're gone. But even as we drift with the local group pulled by the great attractor, there's an even larger motion at work, one that doesn't pull us anywhere, one that pushes everything everywhere outward, a motion so fundamental, so all-encompassing, that it shapes the very fabric of space itself. Gravity pulls. We've talked about that. The Earth pulled by the sun pulled by the galactic core, the local group pulled by the great attractor, everything falling towards something drawn by invisible threads of attraction. But there's another force, one that doesn't pull at all. It pushes, gently, relentlessly. Not with strength, but with patience. And it's been pushing for 13.8 billion years, since the very first moment the universe began. Space itself is expanding, growing, stretching like fabric pulled at the edges. And as it stretches everything in it, every galaxy, every star, every point of light is moving farther apart. Not because they're traveling through space, but because the space between them is growing. It's one of the strangest ideas in all of science, and it took decades for humanity to accept it, because it goes against everything our senses tell us. Space feels fixed, empty, unchanging. A stage where things happen, not something that moves on its own. But space does move. It breathes outward, and it's carrying the universe with it. The story begins in 1929 with a quiet astronomer named Edwin Hubble working at the Mount Wilson Observatory in California. Hubble was studying distant galaxies, measuring their light, trying to understand how fast they were moving. And he noticed something peculiar. Almost every galaxy he observed was red-shifted. Their light was stretched toward longer wavelengths, toward the red end of the spectrum. And the farther away a galaxy was, the more red-shifted its light became. Redshift means motion, specifically motion away from us. It's the Doppler effect, again the same principle that makes a siren's pitch drop as an ambulance drives past. When a source of light moves away, its waves stretch. When it moves toward us, they compress. So, Hubble's observation meant one thing: distant galaxies were moving away from us. And the farther they were, the faster they were receding. At first, it seemed impossible. Why would everything in the universe be fleeing from us? Were we at the center of some cosmic evacuation? Were we somehow repelling everything around us? No. The answer was far stranger. The galaxies weren't fleeing. Space itself was expanding. And as space grew, it carried the galaxies with it like dots painted on the surface of a balloon being inflated. Every dot moves away from every other dot, not because the dots are moving, but because the surface itself is stretching. This was the birth of modern cosmology, the realization that the universe is not static, not eternal and unchanging as people had believed for thousands of years, but dynamic, growing, evolving. And if the universe is expanding now, that means it was smaller in the past, denser, hotter. If you trace the expansion backward all the way to the beginning, you arrive at a single point, a moment when everything in the universe was compressed into an infinitely small, infinitely hot state, the Big Bang. Not an explosion in space, but an explosion of space itself, the birth of everything. Time, matter, energy, distance, all of it beginning in that first instant, 13.8 billion years ago. Hubble didn't discover the Big Bang. That came later. But his observation that the universe is expanding was the first real evidence that the universe had a beginning, that it wasn't eternal, that it was young in cosmic terms, still unfolding. Now, here's where it gets even stranger. For most of the 20th century, scientists assumed the expansion of the universe would eventually slow down. Gravity, they thought, would act like a brake, pulling everything back together. Maybe not stopping the expansion entirely, but at least slowing it, gradually, over billions of years. But in 1998, two teams of astronomers made a discovery that shocked the world. They were studying distant supernovae, exploding stars that act as cosmic lighthouses, bright enough to be seen across billions of light years. By measuring the brightness and redshift of these supernovae, the astronomers could calculate how fast the universe was expanding at different points in its history. And they found something no one expected. The expansion wasn't slowing down. It was speeding up, accelerating. Somehow, the universe was expanding faster now than it was billions of years ago. Something was pushing space apart, overpowering gravity, driving everything farther and farther away from everything else. They called it dark energy. Not because they knew what it was, but because they didn't. It's dark because it's invisible, undetectable, except through its effects. And energy because it seems to fill all of space, exerting a kind of pressure that drives expansion. To this day, no one knows what dark energy is. It makes up about 68% of the total energy in the universe, more than matter, more than stars, planets, black holes, and galaxies combined. And yet, we can't see it, can't touch it, can't even measure it directly. We only know it's there because the universe is expanding faster than it should. Think about that for a moment. The most abundant thing in the universe, the thing that makes up more than 2/3 of everything, and we don't know what it is. It's one of the great mysteries of science, one of the deepest questions we've ever asked. And we're still looking for answers. But here's what we do know. Dark energy is winning. Gravity pulls galaxies together. Dark energy pushes space apart. And at large enough scales, dark energy is stronger. It's not strong enough to tear apart the local group. We're too close, too tightly bound by gravity. But beyond the local group, beyond the gravitationally bound clusters, dark energy dominates. And as time goes on, it will dominate more and more. Right now, galaxies outside our local neighborhood are moving away from us. In 1 billion years, they'll be farther. In 10 billion years, farther still. Eventually, they'll be so far away that their light will never reach us again. They'll cross what's called the cosmic event horizon, a boundary beyond which nothing, not even light, can travel back to us. And when that happens, those galaxies will disappear from the universe. Not because they've been destroyed, but because the space between us and them has grown so much that we can never see them, never reach them, never know they exist. Future astronomers living billions of years from now will look out into the night sky and see almost nothing. Just the local group, just the merged remnants of the Milky Way, and Andromeda glowing alone in a vast, empty darkness. They might never know there were other galaxies, other stars, other worlds. The evidence will have drifted beyond the horizon, carried away by the expansion of space. Unless, of course, they find records, messages, data left behind by earlier civilizations like ours, who could still see the full scope of the cosmos. In a way, we're living in a golden age, a time when the universe is still visible, still filled with light, still young enough that we can look out and see galaxies billions of light years away, trace their motion map, their history. But that age is ending, slowly, gently, the way all things in the universe end not with violence, but with distance, with silence, with the slow drift into isolation. Now, let's return to Hubble's discovery, the idea that distant galaxies are moving away from us. Some people hear this and think, does that mean we're at the center of the universe, that everything is fleeing from us? No, that's a common misconception. The expansion of space is the same everywhere. No matter where you are in the universe, you would see the same thing, distant galaxies moving away from you, with farther galaxies receding faster. It's not that we're at the center, it's that there is no center. Imagine the surface of a balloon again. As the balloon inflates, every point on the surface moves away from every other point. If you were an ant standing on one dot, you'd see all the other dots moving away from you. But if you move to a different dot, you'd see the same thing. Every location looks like the center because the expansion is uniform. That's what's happening with the universe. Space is expanding equally in all directions. There's no edge, no center, just growth everywhere all at once. It's hard to picture. Our minds want to imagine the universe as a sphere expanding into something. But that's not quite right. The universe isn't expanding into anything. It's just growing, creating more space, more distance, more room. And here's another strange detail. The speed at which distant galaxies are moving away from us can exceed the speed of light. Wait, didn't Einstein say nothing can move faster than light? Yes, but there's a loophole. Einstein's rule applies to objects moving through space. A spaceship, a particle, a beam of light, none of these can travel faster than light relative to the space they're moving through, but space itself. Space doesn't have that limitation. Space can expand as fast as it wants. And if space is expanding fast enough, then objects embedded in that space can appear to be moving away from us faster than light. Not because they're traveling through space, but because the space between us is growing so quickly. It's like standing on one end of a long conveyor belt while someone else stands at the other end. Even if you're both standing still, the belt can carry you apart faster than you could ever run. Right now, there are galaxies so far away that their light, which left them billions of years ago, is only just reaching us. And there are other galaxies even farther whose light will never reach us because the space between us is expanding faster than light can cross it. Those galaxies are beyond the observable universe, not because they don't exist, but because we can never see them. The expansion has carried them beyond reach. The observable universe, the part we can see, has a radius of about 46 billion light years. But the actual universe, it could be far, far larger, infinite even. We'll never know because we can only see as far as light has had time to travel since the Big Bang. Beyond that, mystery, darkness, and unknowable vastness. Does that make you feel small, or does it fill you with wonder? Maybe both. That's the paradox of astronomy again. We're tiny, insignificant, standing on a pale blue dot in an unimaginably vast cosmos. And yet, we're here, conscious, aware, able to ask questions, able to look out into the dark and measure the expansion of the universe itself. That's no small thing. And here's the beautiful part. Even as the universe expands, even as galaxies drift away, even as dark energy pushes everything apart, none of it changes the way we experience the world. The Earth still spins, the sun still rises, the seasons still turn. The expansion of space is so slow, so gentle that it only matters at the largest scales. On human scales, on planetary scales, even on galactic scales within the local group, gravity holds things together. The expansion passes us by like a whisper we can measure, but not feel. We are passengers on a ship that's drifting away from all the other ships. But inside life goes on, the same, unchanged, protected by the bonds of gravity, by the smallness of our corner of the universe. And yet, knowing we're drifting, knowing the universe is expanding, that space itself is growing, it changes something, doesn't it? It adds a layer of meaning, a sense of impermanence, a reminder that nothing lasts forever, not even the cosmos. But even as space expands, pulling galaxies apart, there's one final motion we haven't talked about yet. The strangest one of all, the motion that ties everything together. The speed at which we're truly moving, when you add up all the layers, all the spins and orbits and drifts and measure them against the oldest thing in the universe, the faint glow of the Big Bang itself. So, let's add it all up. The Earth spins at over 1,000 miles per hour at the equator. It orbits the Sun at 67,000 miles per hour. The solar system flies through the Milky Way at 514,000 miles per hour. The Milky Way rushes toward Andromeda at 250,000 miles per hour. The local group drifts toward the Great Attractor at over 1 million miles per hour. And on top of all that, space itself is expanding, carrying everything away from everything else. When you add it all together, every spin, every orbit, every drift, every pull, scientists estimate we're moving at roughly 1.3 million miles per hour relative to the cosmic microwave background, the faint afterglow of the Big Bang itself. 1.3 million miles per hour. That's 370 miles every second. Fast enough to circle the Earth in 2 minutes. Fast enough to reach the moon in less than an hour. And you feel nothing. Not a breeze, not a tremor, not the slightest hint of motion. You're sitting or lying down, perfectly still. The air around you is calm. The coffee in your cup doesn't ripple. The stars outside your window seem fixed, eternal, unchanging. How is that possible? The answer lies in one of the most fundamental principles in physics, the principle of relativity. And it's been understood in different ways for hundreds of years. Galileo was the first to articulate it clearly. In the early 1600s, he imagined a ship sailing smoothly across a calm sea. Inside the ship's cabin, he said you could perform any experiment you liked, drop a ball, toss a coin, watch a fly buzz around, and you'd get the same results whether the ship was moving or standing still. There would be no way from inside the cabin to tell if you were moving, because motion, when it's constant, when it's smooth, with no acceleration or deceleration, is invisible to the people inside it. This is what physicists call an inertial reference frame, a space where the laws of physics work the same way regardless of how fast you're moving, as long as that motion is uniform. The Earth is that ship. The solar system is that ship. We're all inside moving together, and because everything around us is moving at the same speed in the same direction, there's nothing to compare ourselves to. No frame of reference to tell us we're moving. Imagine you're on a train moving at a constant 100 miles per hour. The train is so smooth, so steady, that if you close the curtains and sit still, you can't tell you're moving. You could read a book, drink tea, balance a coin on its edge. Everything behaves as if the train is stationary. But then the train hits the brakes. Suddenly you lurch forward. The tea spills. The coin falls. Now you feel it. Now you know you were moving. The difference, acceleration. Change in motion. That's what we feel. Not motion itself, but the change. The Earth spins at a constant rate. It orbits at a constant speed. The solar system drifts through the galaxy at a constant pace. All of it smooth, steady, unchanging. So we feel nothing. But here's where it gets interesting. What if the Earth's spin suddenly stopped, not gradually, not over millions of years, but instantly? What would happen? The answer is catastrophic. Everything on the surface, people, buildings, trees, oceans, would keep moving at 1,000 miles per hour, the speed the Earth was spinning before it stopped. We'd all be flung forward like passengers in a car that hits a wall. The oceans would surge across the continents, carrying tsunamis larger than mountains. The atmosphere would keep moving, creating winds so powerful they'd strip the surface bare. The ground would crack and buckle. Earthquakes would ripple across every tectonic plate. And then, assuming anything survived, the days would change. One side of the Earth would face the sun for 6 months. The other side would be in darkness for 6 months. Temperatures would swing to extremes. Life as we know it would end. But that's not going to happen. The Earth's spin is stable, protected by something called the conservation of angular momentum. Once something starts spinning, it keeps spinning unless acted upon by an external force. And in the vacuum of space, there's very little to slow the Earth down. Still, the thought experiment reveals something important. We don't feel motion because we're part of it. We're moving with the Earth, with the solar system, with the galaxy. And as long as that motion is constant, it's invisible. But what about the expansion of space? That's not constant, it's accelerating. Shouldn't we feel that? No. And here's why. The expansion of space only matters at the largest scales. Scales where gravity is too weak to hold things together. Between galaxy clusters, between superclusters. in the vast voids where nothing exists but the faint hum of dark energy. On smaller scales, inside galaxies, inside solar systems, inside atoms, gravity and other forces are strong enough to resist the expansion. Space isn't stretching here, it's stable, bound. So, even though the universe is expanding all around us, we don't feel it. The Earth isn't getting bigger. The distance between the Earth and the Sun isn't increasing. The atoms in your body aren't being pulled apart. You're safe, held together by forces much stronger than the gentle push of dark energy. Now, here's a question. If motion is invisible when it's constant, how do we even know we're moving? The answer is observation, measurement, comparison. We see the sun rise and set. That tells us the Earth is spinning. We watch the stars shift position over the course of a year. That tells us the Earth is orbiting. We measure the Doppler shift of distant galaxies. That tells us the Milky Way is moving through space. We can't feel motion, but we can see its effects. And from those effects, we can reconstruct the entire dance, the spins, the orbits, the drifts, the falls. It's like being a detective. You arrive at a scene where everything looks still, but if you look closely, you can see clues, tracks in the dust, patterns in the stars, shifts in the light. And from those clues, you can deduce that motion is happening, even if you can't feel it. In 1887, two scientists named Albert Michelson and Edward Morley tried to measure the Earth's motion through space directly. They believed space was filled with a substance called the ether, an invisible medium that light waves traveled through the way sound waves travel through air. If the ether existed, they reasoned then, the Earth's motion through it would create a kind of wind, an ether wind that would affect the speed of light. Light traveling in the direction of Earth's motion would move slightly faster. Light traveling against it would move slightly slower. So they built an incredibly sensitive device called an interferometer to measure the difference. They found nothing. No wind, no difference in the speed of light. At first, it seemed like a failure, but it turned out to be one of the most important experiments in the history of science, because it proved that the ether didn't exist. That light didn't need a medium to travel through, and that the speed of light was the same in all directions no matter how fast you were moving. This result baffled scientists for years. It didn't make sense. If the Earth was moving through space, why didn't that motion affect the speed of light? The answer came in 1905 from a young patent clerk named Albert Einstein. Einstein proposed something radical, that the speed of light is always the same no matter how fast you're moving. It's a universal constant. And if that's true, then time and space themselves must be flexible, adjusting to keep the speed of light constant. This was the birth of special relativity. The idea that time can slow down or speed up depending on how fast you're moving, that distances can stretch or shrink, that simultaneity to events happening at the same time is relative, not absolute. It sounds like science fiction, but it's been proven over and over again in experiments and observations. GPS satellites, for example, have to account for relativistic effects. Time runs slightly faster in orbit than it does on the surface of the Earth, because the satellites are moving faster and experiencing weaker gravity. If we didn't correct for this, GPS would be off by miles within a single day. So, motion doesn't just shape our experience of the universe, it shapes time itself. The faster you move, the slower time passes for you, relative to someone standing still. Astronauts on the International Space Station, orbiting at 17,500 miles per hour, age very slightly slower than people on Earth. The difference is tiny fractions of a second over a lifetime, but it's real, measurable. If you could somehow travel at a significant fraction of the speed of light, say 90% of light speed time would slow down dramatically. A journey that takes 1 year for you might take 10 years for someone back on Earth. You'd arrive having aged only 1 year while a decade had passed for everyone else. This is called time dilation. And it's one of the strangest, most beautiful consequences of motion. That time is not fixed, that it flows at different rates depending on where you are and how fast you're moving. But let's return to the question at hand. Why don't we feel motion? Part of the answer is physics. Motion is invisible when it's constant. We only feel changes, acceleration, and deceleration turns. But part of the answer is biology. We evolved on a spinning planet. Our senses developed in a world where motion was the norm, not the exception. So our brains learned to ignore it, to filter it out, to focus on what's changing, not what's constant. Think about it. You don't feel the earth spinning because you've been spinning with it since before you were born. Your inner ear, which detects motion and balance, calibrates itself to the world around you. And in your frame of reference, the world isn't moving. It's still. It's the same reason you don't feel the blood flowing through your veins, or the neurons firing in your brain, or the atoms vibrating in your body. These motions are constant. Background. Part of the baseline your senses ignore. But when something changes, when you stand up too quickly or spin in a circle or ride a roller coaster, that's when you feel it. That's when your senses wake up and say, something's different. The universe is full of motion, endless, unceasing layered motion. But from our perspective, standing on the surface of the earth, it all feels like stillness, like peace, like home. And maybe that's the most profound lesson of all. That stillness and motion are not opposites. They're perspectives. Two ways of seeing the same thing. From one perspective, you're sitting still at rest, unmoving. From another perspective, you're hurtling through space at over 1,000,000 miles per hour, spinning and falling and drifting through an endless cosmic dance. Both are true. Both are real. It just depends on where you're standing. But there's one final layer to this. One last piece of the puzzle. Because even with all this motion, all these spins and orbits and drifts, there's still a deeper question we haven't answered. A question that ties everything together. What does it all mean? Not just how we move, but why. And what does our motion through the universe tell us about our place in it? We've traced the Earth's journey through space. Layer after layer of motion, each one nested inside the next, like Russian dolls made of velocity and time. The spin, the orbit, the drift through the galaxy, the fall toward Andromeda, the pull toward the great attractor, the expansion of space itself. 6 different motions all happening at once, all carrying us through the universe at speeds we can barely comprehend. And yet, here you are, still, quiet, resting. How is it possible to move so fast and feel so still? We've talked about the physics, the relativity, the constant velocity, the shared frame of reference. But there's something deeper here, something worth pausing over, because the truth is stillness and motion aren't separate things. They're not opposites. They're two faces of the same reality seen from different perspectives. And understanding that, really understanding it, changes the way you see everything. Let's start with something simple. Right now, you're probably sitting or lying down. From your perspective, you're not moving. The world around you is stable, fixed, real. But zoom out. Look at yourself from space. Now you're spinning, with the Earth rotating once every 24 hours. Zoom out further. You're orbiting the sun at 67,000 miles per hour. Further still, and you're flying through the Milky Way faster than any human spacecraft has ever traveled. So, which is true, are you still or are you moving both? Simultaneously. It just depends on your point of view. This is what physicists mean when they talk about frames of reference. There's no absolute motion, no universal stillness, only motion relative to something else. From the sun's perspective, the Earth is moving. From the Earth's perspective, the sun is moving. Both are correct. Both are valid. Neither is more true than the other. It's like watching a boat drift down a river. From the shore, the boat is moving. But if you're standing on the boat, the shore is moving. Both perspectives are real. Both describe the same event. And this applies to everything in the universe. There's no fixed point, no cosmic anchor, no place you can stand and say, here. This is where everything else is measured from. Even the cosmic microwave background, the faint afterglow of the Big Bang, the oldest light in the universe, isn't truly stationary. It's just the closest thing we have to a universal reference frame. a backdrop against which we can measure our motion. And when we do that, when we measure our speed relative to the CMB, we find that we're moving at about 1.3 million miles per hour in the direction of the constellation Leo. But here's the thing, someone in another galaxy measuring their speed relative to the same cosmic background would get a different number, a different direction, because they're in a different frame of reference. There's no center to the universe, no edge, no place that's more still than any other. Just an endless web of motion, all relative, all interconnected. So, when we say the Earth is moving, what we really mean is the Earth is moving relative to something else. The sun, the galaxy, the cosmic background. But in its own frame of reference, the Earth is perfectly still. And so are you. This isn't just abstract physics. It has real practical implications. For example, think about the astronauts on the International Space Station. They're orbiting the Earth at 17,500 miles per hour. But from their perspective inside the station, they're floating, weightless, still. If they look out the window, they see the Earth rushing past below them. But if they close the window, if they focus on the interior of the station, nothing seems to be moving. They can eat, sleep, work, play all as if they're stationary. The motion is real, but it's also invisible because they're part of it. Or think about the Voyager 1 spacecraft launched in 1977, now more than 14 billion miles from Earth. It's traveling at 38,000 miles per hour relative to the sun. But if you were somehow standing on Voyager looking around you, wouldn't feel like you were moving. The stars would seem fixed. The darkness around you would seem still. Motion is everywhere, but stillness is just as real. And maybe that's the lesson. That stillness isn't the absence of motion. It's motion that's so constant, so smooth, that it becomes indistinguishable from rest. The Earth spins. But because we spin with it, we experience stillness. The solar system drifts through the galaxy. But because we drift with it, we experience stability. The universe expands. But because we're embedded in it, we experience a cosmos that feels unchanging, eternal, solid. Stillness, in other words, is a gift, a grace, a consequence of being part of something larger than yourself. Now, let's take this idea even deeper, because motion doesn't just shape our experience of space. It shapes our experience of time. We've already touched on this Einstein's theory of relativity, the idea that time flows at different rates depending on how fast you're moving. But it's worth exploring further because it's one of the most beautiful, most profound insights in all of science. Time, as it turns out, is not a river that flows at the same rate for everyone. It's more like a landscape with hills and valleys where some places time moves faster and others slower. The faster you move through space, the slower you move through time. And the stronger the gravity around you, the slower time flows. This has been proven again and again in experiments. Atomic clocks on airplanes tick slightly faster than clocks on the ground. Clocks on GPS satellites orbiting high above the Earth, where gravity is weaker, run faster still. If we didn't account for these differences, if we ignored relativity, GPS would be useless. The errors would accumulate so quickly that your phone wouldn't be able to tell where you were. So, time dilation isn't just a theoretical curiosity. It's a practical reality woven into the technology we use every day. But here's where it gets strange. From your perspective, your own clock always ticks at the same rate. You never experience time slowing down or speeding up. It's only when you compare your clock to someone else's, someone moving at a different speed or experiencing different gravity, that you see the difference. So, in a sense, time is relative too, just like motion, just like stillness. There's no absolute time, no universal clock ticking away somewhere in the cosmos. Only time is experienced by each observer in their own frame of reference. This might sound unsettling, like the universe is unstable, shifting, unreliable. But it's actually the opposite, because even though time and space are flexible, the laws of physics are constant. The speed of light is the same for everyone. The equations that describe motion, gravity, energy, they work the same way everywhere for everyone always. So there's a deeper stability beneath the apparent chaos, a structure, an order. And maybe that's what stillness really is. Not the absence of motion, but the presence of order. The sense that even as everything moves, even as time flows at different rates and space expands and galaxies drift apart, there's still a pattern, a logic, a coherence. The universe is a dance. And like any dance, it has rhythm, structure, beauty, even if the dancers are moving too fast to see. Now, here's a question. Worth asking, does any of this matter? Does it change your life to know that you're spinning at 1,000 miles per hour, that you're orbiting at 67,000, that you're drifting through the galaxy at 500,000? In one sense, no. The Earth will keep spinning whether you think about it or not. The stars will keep drifting whether you measure them or not. Your life, your daily routines, your relationships, your joys and sorrows, none of that depends on understanding cosmic motion. But in another sense, yes, it matters deeply. Because knowing you're in motion, really knowing it, feeling it in your bones, changes the way you see yourself, the way you see your place in the universe. You're not separate from the cosmos. You're part of it, woven into its fabric, moving with it, carried by it, shaped by it. Every breath you take, every thought you think, every moment you experience, it's all happening while you're flying through space at over 1,000,000 miles per hour. While the Earth spins and the sun orbits and the galaxy drifts and the universe expands, you are motion and you are stillness, both at once. And maybe that's the deepest truth of all, that you don't have to choose between them, that they're not contradictions but complements. Two ways of being that exist together seamlessly, naturally. You can be still in your heart while moving through the cosmos. You can be at peace while the universe rushes around you. You can rest while the Earth carries you forward into an unknowable future. Because stillness isn't about stopping. It's about acceptance. About being present wherever you are, however fast you're moving. The Earth doesn't resist its spin. The sun doesn't fight its orbit. The galaxies don't struggle against their drift. They simply move, gracefully, effortlessly, as if motion and stillness were the same thing. And, in a way, they are. Because if you're moving at a constant speed in a straight line, with nothing to disturb you, then from your perspective, you're not moving at all. You're at rest, at peace, in a state of perfect eternal stillness. That's the paradox. That's the gift. You're always moving, and you're always still. Both are true. Both are real. Both are part of what it means to be alive, to be conscious, to be a small piece of the universe looking back at itself. So, as we reach the end of this journey, as we trace the final threads of motion that carry us through the cosmos, there's one last thing to consider. Not just how we move or why we move, but what it means. What all this motion tells us about who we are, where we came from, and where we're going. We've traveled far tonight. Not through space, though. We've crossed billions of light years in imagination. Not through time, though we've touched moments separated by eons. We've traveled through layers, through the nested motions that carry us, unknowing, through the cosmos. The Earth spinning beneath your feet, the sun pulling you in an endless ellipse, the galaxy sweeping you through starlit currents, Andromeda approaching patient and inevitable, the great attractor calling from beyond, and space itself breathing outward, stretching the fabric of everything. 6 motions, 6 dances, all happening at once, all invisible, all real. And through it all, you've remained still. Perfectly, impossibly still. How strange it is, isn't it, to move so fast and feel nothing, to be part of a cosmic ballet and never hear the music. But maybe that's exactly as it should be, because if we felt every motion, every spin, every orbit, every drift, we'd be overwhelmed, dizzy, lost in the chaos of velocity. Instead, the universe gives us stillness, not as a lie, but as a gift. A way to experience peace even while flying through the dark at speeds that would make light seem slow. And isn't that what life is really? A constant balancing between motion and stillness, between change and stability, between the rush of time and the quiet moments where everything feels eternal. We spin through our days orbiting our routines, drifting through years. And yet, in the quiet moments when we pause, when we breathe, when we simply exist, we find stillness. Not because the motion has stopped, but because we've learned to move with it instead of against it. The Earth teaches us this. It spins without resistance. It orbits without complaint. It drifts through the galaxy as if motion were the most natural thing in the world. And it is. Motion is natural. It's the default state of the universe. Everything moves. Everything changes. Everything flows. But stillness. Stillness is just as natural. It's what happens when you stop fighting the motion, when you accept it, when you become part of it. Think about the astronauts floating in the space station. They're moving faster than a speeding bullet orbiting the Earth 16 times a day. But inside the station, they float, weightless, at peace. They're not fighting gravity. They're surrendering to it, falling eternally around the Earth. And in that constant fall, they find weightlessness, stillness. The same is true for all of us. We're falling through space carried by forces we can't see toward destinations we'll never reach. But we don't have to fight it. We can surrender to the motion, accept it, find stillness within it. And maybe that's the deepest lesson the cosmos has to teach us. Now, let's pull back one more time. Let's look at the whole picture. 13.8 billion years ago, the universe began. Not as an explosion in space, but as an explosion of space itself. Everything that exists, every atom, every particle, every bit of energy, it all came from that first moment, that first breath. And ever since, the universe has been moving, expanding, growing, evolving. Stars ignited and died, galaxies formed and merged, planets coalesced from dust and gas. And somewhere on one small world orbiting an ordinary star in an unremarkable galaxy, life began. Not just any life, conscious life. Life that could look up at the stars and wonder. Life that could measure the spin of the Earth, the orbit of the sun, the drift of the galaxies. Life that could trace its own motion through the cosmos. That life is you. You are the universe looking back at itself. A small piece of cosmic dust organized in such a way that it can think, feel, dream, wonder. And in doing so, you've discovered something remarkable, that you're not separate from the universe. You're part of it, made from it, woven into its motion, its structure, its story. Every atom in your body was forged in the heart of a star that died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it came from stars that lived, burned, and exploded, scattering their remains across the galaxy. You are quite literally made of stardust, and that stardust is moving, has always been moving, will always be moving. So when you feel still, remember you're not. You're spinning, orbiting, drifting, falling through space at speeds beyond comprehension. But you're doing it so smoothly, so gracefully, that it feels like rest. And when you feel lost in the chaos of life, remember the universe is chaotic too, full of motion, change, unpredictability. But beneath it all, there's order, patterns, laws that hold everything together. Gravity pulls, light travels, time flows, and you small, fragile, temporary, you exist within all of it. Part of the pattern, part of the dance. Does that make you insignificant, or does it make you miraculous? Both maybe. That's the paradox again. You're tiny. A speck, a brief flicker of consciousness in an unimaginably vast cosmos. And yet, you're the only thing in the universe that can understand the universe. The only thing that can look up and say, I know where I am. I know how fast I'm moving. I know what it all means. That's not insignificant. That's extraordinary. So as we come to the end of this journey, here's what I want you to take with you. You are always moving, always, even when you feel still. especially when you feel still. You are part of something vast, a cosmic dance that's been going on for billions of years and will continue for billions more. And you are both infinitely small and infinitely important. A grain of sand on an endless beach, a drop of water in an infinite ocean. And yet without you, the universe would be less, quieter, emptier. Because you are the part of the universe that notices, that cares, that wonders. So keep wondering, keep looking up, keep asking questions about where you are, how you got here, where you're going. Because the answers, strange, beautiful, impossible as they are, they're worth knowing. They change the way you see the world, the way you see yourself, the way you experience the simple act of being alive. You've never stood still, not for a single breath, not since the day you were born, and you never will. But that's okay, because motion, when you stop resisting it, becomes grace, becomes peace, becomes a kind of stillness all its own. The earth spins, the sun orbits, the galaxies drift, and you, small, fragile, miraculous you move with them. Part of the dance, part of the flow, part of the endless, ancient, beautiful motion of the cosmos. So rest now. Let the motion carry you. Let the universe hold you in its invisible arms, spinning you gently through the dark. You don't need to understand everything. You don't need to hold on tight. You just need to be here, present, aware, grateful for this brief moment of consciousness in an unconscious cosmos. Because that's enough. That's more than enough. That's everything. We've drifted through space and time tonight, tracing the hidden paths that carry us through the universe. From the spin of the Earth to the expansion of space itself, we've seen that motion is everywhere. And yet, in the midst of all that motion, we find stillness. Thank you for traveling with me, for listening, for wondering, for being curious about the cosmos and your place in it. The universe has so many more stories to tell, so many more mysteries to unravel, and I'll be here ready to explore them with you one quiet night at a time. Until then, sleep well, dream gently, and remember, even in your deepest rest, you're dancing through the stars. Good night.